Welcome to Unit 3 Trigonometry, Trigonometric Identities, Chapter 6. This is the last chapter of the trig unit. In this section, you'll be able to develop trigonometric reasoning by proving trigonometric identities using reciprocal identities, quotient identities, Pythagorean identities, sum or difference identities, and these will be restricted to sine, cosine, and tangent, as well as double angle identities with the same restrictions. There are many algebraic relationships between trig functions known as identities. These identities allow for the simplification of complex trigonometric expressions as well as for solving trigonometric equations. Here's a checklist for this section. Part 1, reciprocal, quotient, and Pythagorean identities. Again, notes and the accompanying practice from your textbook, along with the videos, as you are obviously aware of. Part 2, sum, difference, and double angle identities. Part 3, proving an identity, and Part 4, solving trig equations using identities. There'll be an identities review, that's a formative assessment, not for marks, and then also a curriculum review and quiz in this section. When this is done, and all of the prior checklist components have been completed, there'll be a final summative assessment at the end of the trigonometry unit. Okay, so let's get right into this. This is arguably the more difficult of all of the trig sections, but the most fun when you get into it, in my opinion. Okay, part 1, reciprocal, quotient, and Pythagorean identities. So identities are equations that are valid for all permissible values of the variable, but on both sides of the equation. To prove an identity means to algebraically show that the left side is the same as the right side. To verify an identity means to show that the left side and right sides are numerically equal for a specific value. Although an equal sign is present, the rules for equations, so adding or multiplying both sides by the same amount, or moving things from one side to another, are not used. You will simply transform each side individually until they are equivalent. To accomplish that, you're going to consider the suggestions given. So, some of this might seem a little strange right now, but once we get into proving the identities, these steps will become invaluable. So, they are: replace trig ratios with equivalent expressions that contain sine and cosine. Look for forms of Pythagorean identity that can be replaced. Manipulate the expressions algebraically. You may have to use factoring or creation of common denominators, or multiplying by an expression that would make that's equivalent to 1. These are the most common methods. You might have to be inventive or creative. There's more than one way to show that two expressions are the same. If one thing doesn't work, try something else. With practice, these conversions will become familiar and accomplished with ease. When asked to prove or show that one side actually equals the other, one side seems more complex, try working with the side that's more complex. Once an identity has been proven, it can be used to prove other identities. The following identities have already been proven and may be used freely. They can be found in the formula sheet in the resource section of the website, so memorization of them is not required. You should, however, be able to recognize them when you see them, so it is good to know what they are. Okay, we'll start with the reciprocal identities. You've already kind of seen these a couple chapters ago. So sine theta is 1 over cosecant, cos is 1 over secant, and tan is 1 over cotangent. And the reverse is also true. Cosecant is 1 over sine, secant is 1 over cos, and cotangent is 1 over tan. Alright, so we'll move on because we already know those ones. Quotient identities. So quotient, of course, means division. So instead, tan can also be written as sine theta over cos theta. Now remember back in the unit circle, we had tan theta equals y over x. Well, remember that the y value is similar to sine on the unit circle, and the x value is the same as cosine on the unit circle. Okay, so that's where that guy comes from. And of course, the reciprocal is also true, so if tan is sine over cos, then cotangent must be cos over sine. The advantage of the reciprocal and quotient identities is they allow you to rewrite any of the other four ratios in terms of sine and cosine. Most of your trig identities are going to be in terms of sine and cosine, so the more often you can write them in those terms, the easier this will be. Let's use some examples. Given the equation cosecant theta equals cotangent theta divided by cos theta, determine any non-permissible values of theta. So non-permissible values, of course, occur when the denominator cannot be 0. Okay, so let's do the first. Cosecant theta is the same as 1 over sine theta. So sine theta cannot be 0, which means that theta cannot equal 0, pi, and 2 pi. So any multiple of pi. Okay, good. Whole number multiple of pi, I guess I should say. And we have cos theta can also not be 0 because it's in the denominator. So theta would be pi over 2, 3 pi over 2, and so on. So any whole number multiple of pi over 2 will give you non-permissible values. Okay, awesome. Verify the equation for pi over 3. So again, verify means just to substitute in and show that numerically the left side equals the right side. So we have cosecant of pi over 3 equals cotangent of pi over 3 divided by cos of pi over 3. Cosecant is the reciprocal of sine, so sine of pi over 3 is root 3 over 2, so cosecant would be 2 over root 3. Okay? Cotangent of pi over 3 is the reciprocal of tan, so that would be 1 over root 3. And cosine of pi over 3 is 1/2. Okay? So we have 2 over root 3 equals, if we flip 1 over root 3 and divide it by 1/2 to 1 over root 3 times 2 over 1, flip and multiply, we also get 2 over root 3. So because the left side and the right side are numerically the same, the identity is verified for pi over 3. Part C, verify the equation graphically using technology. So, take out your calculator. In Y1, graph cosecant theta if you have an Inspire, or if you have an 84 version, type in 1 divided by sine x. In Y2, I want you to type in 1 divided by tan x in brackets divided by cos x. Okay? Then, again, if you need to pause the video in order to do that, go ahead. When you're finished, turn it back on and you'll see that here are your graphs. Okay, the first one is cosecant of x. The second one is cotangent x over cos x. And if you'll notice, they look pretty much the same. So I graphed them overlying one another, and as you can see, they are identical. So, seemingly, graphically, verifies that it also works as an identity. Okay, part D. Prove the equation is an identity for all permissible values of theta. So, to do this, we have to use our reciprocals and our quotients. So, we know that cosecant is 1 over sine theta. Cotangent is cos over sine, and that's divided by cos theta. So we're going to work with the right-hand side because it seems a little more complicated. So I'm going to flip the denominator, cos theta over 1, and multiply it by the numerator. If you'll notice then, the cosines would cancel, and we're left with 1 over sine theta equals 1 over sine theta. Good. So it is an identity for all values of theta that are permissible. Okay, simplify the expression tan theta cos theta over secant theta cotangent theta. Okay, so again we're going to write these in terms of tan or sine and cosine as often as possible. So tan is the same as sine theta over cos theta times cos theta, and I'll just put that over 1 so it looks like a fraction, all over secant is 1 over cos theta, and cotangent is cos theta over sine theta. Okay, if you notice in the numerator, the cos thetas will cancel, so that simplifies to sine theta over 1, or just sine theta. On the bottom, The cos thetas cancel, and it simplifies to 1 over sine theta. So sine theta divided by 1 over sine theta means to take the denominator and flip and multiply. So sine theta over 1 times sine theta over 1 gives me sine times sine is sine squared theta. 1 times 1 is 1. Sine squared theta divided by 1, still sine squared theta. Please note where I put the squared on the sine theta. Again, sine squared theta is the same thing as sine theta all squared. Okay? Good. Nice little notation for you to make things simpler. Okay, awesome. There's your graphs. And I'll skip on to Pythagorean identities. Okay, these are called Pythagorean identities because they follow the same format as the Pythagorean theorem, a squared plus b squared equals c squared. There are 3 of them. One involves sine and cos, one tan and secant, and one cotan and cosecant. So, prove the Pythagorean identities. Okay. If we look back at our formula, r squared equals x squared plus y squared, okay? Then, if we use the unit circle, r was 1, x was cos, and y was sine. So, there's the first identity proven. 1 squared is just 1 equals cos squared plus sine squared. Okay? Great. Now, if I take and divide every single term by cos squared theta, okay, then 1 over cos squared is the same thing as secant squared. Okay, cos divided by cos is 1, and sine divided by cos is the same thing as tan. So sine squared divided by cos squared gives us tan squared theta, and there is our second Pythagorean identity. Now, we can also take 1 equals cos squared theta plus sine squared theta, and instead of dividing by cos squared, we're going to divide everybody by sine squared theta. Remember, in an equation, you can do this as long as you do it to every single term. Now, 1 over sine squared is the same thing as cosecant squared, because that's the reciprocal of sine. Okay, cos over sine is the same as cotangent, so that's cotangent squared. And sine squared theta divided by itself is just 1. And if you notice, that is the same as our third Pythagorean identity. Fun stuff, right? All right, on to the next section. Last little bit here before you get to try this all by yourself. Okay, simplify the following. 1 minus cos squared theta over secant squared theta minus 1. Those look familiar. How can I get 1 minus cos squared theta? Well, if you remember, 1 equals cos squared theta minus plus sine squared theta. So, if I get sine squared theta by itself, I would have to subtract cos squared theta. So, 1 minus cos squared theta is the same thing as sine squared theta. Okay, awesome. Secant squared theta minus 1. That should also ring a bell. If you remember that secant squared theta equals 1 plus tan squared theta, then to get secant squared minus 1, I would subtract the 1 from this side to get secant squared minus 1 equals tan squared theta. So in place of secant squared theta minus 1, I can substitute in tan squared theta. Okay, great. Now I'm going to change my tan squared into sine and cosine. So that gives me sine squared theta over sine squared theta divided by cos squared theta. Okay, flip and multiply. So sine squared theta over 1 times cos squared theta over sine squared theta. Sine squareds cancel, and we're left with cos squared theta as the final answer. Okay, part B. Oh, this one looks good. Okay, notice that we have sine squared theta in both our terms. So I'm going to factor that out, first of all. Okay, so that equals sine squared theta times, sine squared goes into itself once, and it goes into sine squared cos squared. We'll take the sine squared and factor it out, and we're left with cotangent squared theta. Now, 1 plus cotangent squared theta is a Pythagorean identity. That's the same thing as cosecant squared theta. So this is going to equal sine squared theta times cosecant squared theta. But cosecant squared theta is the reciprocal of sine squared. So that's 1 over sine squared theta. And when we multiply something by its reciprocal, we just get 1. All right. Sine squared minus, or sine to the fourth minus cos to the fourth. What are we going to do with that? Well, as it so happens, that looks like a difference of squares. So I'm going to factor that into conjugates. So that becomes sine squared theta plus cos squared theta times sine squared theta minus cos squared theta. Well, sine squared theta plus cos squared theta is the same thing as 1, so that just becomes 1 times sine squared theta minus cos squared theta, okay? Or just sine squared theta minus cos squared theta. All right. Well, that last one's pretty tiny, so here, I'll make it a little bit bigger maybe. All right. So I have two fractions on the top, and I'm trying to add them, so I need a common denominator. I'm just going to use cos theta times sine theta. So my denominator will be cos theta sine theta. So to get that, I would have to multiply both the bottom and the top over on the first term by sine theta. So sine theta times cos theta is that denominator, and sine theta times sine theta gives me sine theta all squared. Plus, to get sine theta to become sine theta cos theta, I'm going to have to multiply both top and bottom by cos theta. So cos theta times itself gives me cos squared theta, all over 1 divided by sine theta. Now, again, sine theta squared plus cos squared theta equals 1, so I'm going to substitute in a 1 over cos theta sine theta, all over 1 over sine theta. I'm going to flip the bottom and multiply it, so I get 1 over cos theta sine theta times sine theta over 1. The sine thetas cancel, so I'm left with 1 over cos theta, which of course is the same as secant theta. Oh, good times. Love this stuff. Okay, so you probably are wanting to practice this. You might want to go to page 296 and work on the questions as assigned. Have fun!